I'm Bevis Hutchinson from the Swedish institute called SwereaKIMAB, and I've been involved in research into vanadium steels for very many years. Together with colleagues, we wrote a monograph on the subject about 15 years ago, and two of us, Rune Langneborny and I, have recently done an update of that document, which has now come out, and this is what it looks like. And what we've done here is to choose four themes out of this fairly lengthy document to exemplify how vanadium is used in steels and the things which it affects and how we control it in our steels. So these themes are in the lines, as you see here, of recrystallization controlled rolling. This is a way of combining good strength and toughness in the products. We want to refer to the influence of nitrogen, which is a very important co-alloying element in vanadium steels, and also some words about carbon, which of course is found in most steels. And then an important phase in vanadium steels is the nitride, vanadium nitride, and this can provide a very useful grain refining agent for ferrite, as we'll show. Finally, the fourth theme relates to high-strength steels of bainitic or martensitic form, where we are showing that you can use vanadium in a different way, but also to increase the strength of the steels. Now, before we start on the technological details, there's one aspect which goes into the fundamentals of thermochemistry, which I'd like to spend a few moments discussing, and that can be seen in this slide here. These lines are solubility product lines for different compounds which are found in microalloyed steels. They're vanadium compounds, they're niobium compounds, and titanium compounds. And in order to use these elements efficiently, we need to dissolve them at high temperature in the steel. And these lines show the solubility conditions for the different compounds. Now, some of them are carbides and some of them are nitrides, and you can see vanadium carbide is a dashed line at the top. That is a very soluble element. But more important for us is the nitride, and it seems when you look at this slide as though that is rather similar to titanium and niobium. They lie together in a cluster. But this is misleading. The niobium and titanium are principally reacting with carbon, whereas in this case vanadium is reacting with nitrogen. Since there's typically 10 times as much carbon as nitrogen in the steel, then this means that the solubility of vanadium is actually very much higher, or approximately 10 times as high as the niobium or titanium. And this relatively high solubility has important influences through the processing of steel and through the precipitation effects which provide the beneficial mechanical properties of the steel. Well, after that introduction in terms of the rather fundamental thermochemistry, I'd like to now give something like a recipe for the best way to produce good properties in the steel when we're using vanadium. And here are a list of points to follow in the recipe. We need to design the deformation schedules of the austenite, that's the rolling at high temperature, in order to obtain the finest possible recrystallized grain size at the end of the hot rolling process. We also need to ensure that the last stages of deformation happen at a sufficiently high temperature that little precipitation of vanadium takes place at this stage. We're going to want it to precipitate, but not yet. We also need, having got a fine grain size, to prevent it from growing, and to do this we need a dispersion of some second phase particles. That's usually titanium nitride, which is a very stable phase. And that will keep the grain size of the austenite fine until we cool it down, and then it will transform in the transformation range. And here we want to get the maximum refinement of the ferrite. So we want to turn this fine austenite grain structure into as fine as possible a ferrite grain structure. That we'll achieve by rapid cooling, but at some stage thereafter we want to slow it down, because then we want to ensure that the transformation is complete and the maximum amount of precipitation of the vanadium carbon nitrides takes place in order to maximize the strength of the steel. So we want to get a fine-grained ferrite with effective precipitation strengthening, which will give us the strength and toughness that we want in the product. If we take a look at this diagram, it's a kind of generic of hot working. It could describe a lot of rolling processes. It might even describe a forging process. We start off by either having a slab which is reheated or a mini-mill billet which is cooled down to the reheating temperature, and at this stage the austenite grain size is very large. It's broken down successively through roughing, through final rolling conditions, and then two different types of approach may be used. Either that rolling can be continued to even lower temperatures whereby recrystallization does not occur, but the grains will become pancaked, as we say. They retain the deformed shape prior to cooling down and transformation. Alternatively, we can stop it with a fine recrystallized structure and cool that through into the ferrite range. And we can apply rapid cooling in different ways. If we want to, it will generally be beneficial. And in the case of strip material, we will rapidly cool and then coil the material, and thereafter the temperature will only cool very, very slowly. Now, vanadium has the characteristic of high solubility, as I talked about earlier, and this means that it has very little interaction with the recrystallization process. An extreme other behavior is seen by a case of niobium in the right-hand diagram. Niobium raises the recrystallization stop temperature very, very strongly. That means if we want to have a deformed pancake structure, niobium is your man. If you want to have a recrystallized austenite grain structure, then vanadium will not interfere with the process. And that is the basis of the recrystallization controlled rolling theory. What are the relative merits of these two processes? Both of them produce excellent products. The recrystallized controlled rolling, RCR, as you can see here, is carried out at higher temperatures, at least towards the end of the rolling, and also because the structure is recrystallized and not deformed, it is softer, and therefore the rolling loads are reduced in this case, as compared to the controlled rolling case. So if you have a mill which is not too strong, then there's an advantage to use recrystallization controlled rolling. It will also reduce to some extent the rate of roll wear. The other advantage of the RCR process is that it's quicker. In order to control roll, it's necessary to allow the steel plate to cool down. That takes time, and in this particular example, you can see that its total rolling time is 8 minutes in the one case and only 3 minutes for the RCR. That's a really important matter when it comes to productivity, of course. If we turn to the quality of the products that are produced from these, they are very comparable with one another. These bar charts here show the yield stress, the tensile stress, and the impact transition temperature. The first one is the RCR process with air cooling. The second bunch are RCR processing with accelerated cooling. And then the third set are for controlled rolling. And you can see that the strength levels are very similar to one another. The impact transition temperature, which should be as low as possible, is somewhat lower in the case of controlled rolling, CR. But all of them are excellent in this regard. So these are two alternative parallel types of processes that can be adopted. In the case of controlled rolling, you would be, generally speaking, using niobium as microalloying element. In the case of recrystallization controlled rolling, then it would be vanadium. Let's take a look now at the cooling after hot rolling. And what does this do for us? Well, one thing we can control is the rate of cooling by blowing air or blowing mist of water and air at the steel. So we can change the rate at which it cools down, particularly important through the transformation range to ferrite. And the left-hand figure here shows us that the ferrite grain size decreases quite markedly as the cooling rate is increased. Now, that's of course a very good thing because finer grain size gives improved strength, but it also gives improved toughness. And this is the only way that we can simultaneously optimize both those important properties. The figure on the right demonstrates the increase in yield stress for a number of steels as the cooling rate is increased in the same range. These are the same experiments. The ferrite grain size I've talked about, that is an important, very important parameter control. But the cooling rate is doing something in addition to this, because during the transformation we are creating the vanadium carbon nitride particles, which are going to give additional strength. And they themselves are dependent upon the cooling rate. We'll come and look at that in a moment, but let's continue with the grain size refinement. This figure here shows the transformation ratio of grain sizes. That is, say, the ratio of the prior austenite grain size to the final ferrite grain size. We would like that to be a large number, because that would mean that the ferrite grain size is getting smaller. And what we can see on these 4 lines are, firstly, the effect of cooling rate, which we've already seen. The lines go up to higher ratios as the cooling rate is increased. But a very interesting additional factor is that as the nitrogen level of the steel is changed, so the transformation ratio also increases. So one of the things that is happening when we add higher nitrogen contents to the vanadium steel is that it's giving us an improved refinement of the ferrite grain structure, getting finer ferrite grains out of a given austenite grain structure. That is one of the many advantages that we will find when we add nitrogen to steels with vanadium. Here are some results. Most of the results I'm showing here are from our own work in Stockholm, but here are some from Professor Yang's group in Beijing, simulating seamless pipe processing, and the effect of nitrogen here can be shown to increase the yield stress. That's good, but at the same time to increase the impact energy, the toughness of the steel is going up. So we have 2 things which are happening here. We're getting a grain refinement, which is improving toughness. We're getting a precipitation strengthening, which is increasing strength. And we want to keep these in some sort of balance so that we don't prejudice the overall properties of the steel. How does the nitrogen affect the precipitation strengthening? Well, it has a very big effect, and you can see this in the TEM micrographs on the left-hand side. Similar steels, but one with only 0.005% nitrogen, and the other with 0.026% nitrogen, 5 times as much. And the rows of particles are plainly much, much denser in the second case. The particles themselves are smaller, and the result of this is a more efficient strengthening. And numerically, that's seen in the right-hand figure here, where we have 2 different steels with different vanadium contents, 0.06% vanadium and 0.12% vanadium. These have been isothermally transformed at different temperatures, so the temperature of transformation is important, and you can see that the lower temperatures, 600 degrees as against 7 and 750, are raising the precipitation strengthening effect in the steel. And you can also see very clearly how the increase in nitrogen content is improving the yield stress. This is, in this case, principally a result of the refinement of the vanadium nitride particles, which are improving the hardness and strength. Now I'd like to turn to an interesting synergy. We've talked about nitrogen, and now I'm going to raise an additional effect of carbon levels. Now, you might well say, well, everybody knows that carbon increases the strength of steels. That's old hat. But actually it isn't true when you come to look at the yield stress of low carbon steels. The conventional wisdom is actually that the carbon content has no effect beyond how it may affect the grain size. The excess carbon will be in the form of perlite, and that may affect and increase the tensile strength of the steel, but not the yield stress. So we wouldn't, according to conventional thinking of HSLA steels, expect the effect of carbon to be at all pronounced here. But it obviously is. We're increasing by something like 150 megapascals as we increase from, say, 0.04% carbon to 0.24% carbon. Now, why is this? The answer turns out to be very interesting. We can see that having a higher carbon content makes for a more dense dispersion of particles. These two TEM micrographs demonstrate how many more particles there are in the higher carbon steel than in the lower carbon steel. So somehow the carbon level is raising the precipitation strengthening effect of the steel. I don't want to go into a lot of details as to why this is the case, but basically we believe the explanation can be seen in this figure at the bottom, which is part of the phase diagram, the very bottom left corner of the familiar iron-carbon phase diagram. And the line which says ferrite plus cementite is the usual line that we refer to, but if there is if the cementite is not formed in the steel and we retain austenite, then the solubility of carbon becomes very much greater. And this increases the driving force for nucleation of the vanadium carbonitride particles. So it's this non-equilibrium effect which is enhanced as we raise the carbon level of the steel. And that's a rather fundamental kind of viewpoint of it, but there is a very important practical message that this effect is of particular relevance for products like forgings, for bars and sections, because these steel products typically have higher carbon levels than plate and strip steels. So it's no wonder that these are the kind of products where we will most often find vanadium as a microalloying element. They are also products which can be finish rolled at high temperature, and that is also a benefit because we don't get preliminary precipitation of vanadium nitride in the austenite. Now I'd like to show you examples of a very interesting phenomenon, something else that can happen if we should have some vanadium nitride precipitation in the high temperature austenite. So far I've been saying we don't want it to happen, but if we have a modest amount of it, then those particles can act as nucleants for ferrite. And here's a beautiful example from the work of my colleague Stanislav Sajak, where there is a particle clearly identified as a vanadium nitride particle by the EDS analysis, with a rosette of 4 grains growing out of it. And we can demonstrate without any doubt that these have nucleated at that particle when we look at the orientations of the grains. There are actually 2 different orientations among the 4 grains, but they are always in a crystallographic relationship to the vanadium nitride phase itself. This is the so-called Baker-Nutting relationship between the carbide phase, or nitride phase in this case, and the ferrite. So if we have some of these particles present, they will act to nucleate ferrite, and that will lead to more ferrite grains, and that will lead to smaller ferrite grains, and therefore an improvement in the mechanical behavior of the steel. Here's a kind of conceptual way that this can be done. At high temperatures during the rolling, we're simply getting recrystallization and grain refinement, as talked about earlier. And then at lower temperatures, we start to get some vanadium nitride precipitation in grain boundaries, but also inside the grains. And those nucleants lead to ferrite grains growing at them and producing a very fine structure. Now, the reason that vanadium nitride particles are so good at doing this is related to the crystal lattice and the lattice parameter. It has a very close relationship to the ferrite, and therefore the energy of the interface is believed to be very low, and that is what you would need to have in order to get a very good nucleation effect. So there are other elements, there, manganese sulfide and austenite that are shown, but the green point here, the vanadium nitride, is almost the ideal structure in order to nucleate ferrite from high temperature austenite. That, as you can see, is quite old work, but comes from Ishikawa in Japan. A good indication that we've been able to understand much better with the help of this. So if we want to use the process of vanadium nitride particles for ferrite grain refinement, what do we have to do? Well, we have to get some precipitation of the vanadium nitride in austenite in order to produce these nucleant particles, but we don't want to have too much. We want to leave as much as possible behind, keeping our powder dry in order to produce a fine precipitation of vanadium carbonitride in the ferrite later on. We want to, if we have to stimulate the process by which the vanadium nitride particles are formed. There are a number of different options. One is that they will form preferentially at grain boundaries. That's pretty much always the case. If we have titanium in the steel, then there will be precursors of titanium nitride, and it's well known that vanadium nitride can form a layer on the surface of that, which will then be a good nucleant. Manganese sulfide inclusions have been shown as other sources, but we don't, generally speaking, want to increase the manganese sulfide inclusion content because that would have other deleterious effects. Dislocations can also act to nucleate vanadium nitride, so some deformation at the lower temperatures in the austenite range should be beneficial. And the other thing is, if we can have a waiting period while the steel is in this lower austenite temperature range, then that will provide more time for the vanadium nitride precipitates to form, and then they can be used during the subsequent cooling thereafter. Now, one production route which is particularly well suited to this, and we give some examples of how this can be used in the benefits of it in seamless pipe production. The left-hand diagram is a bit of a schematic of the temperature time schedule for the steel being processed. First of all, the billet is pierced and hot rolled to dimensions. And then there's quite a long delay, sometimes involving reheating, before the final sizing operation of the pipe is carried out. So it's during this delay that we have a time and a suitable temperature to precipitate vanadium nitride. This can be enhanced, as I said earlier, if we have titanium in the steel. And the effect of this is shown on the right-hand picture here, where the ferrite grain size is shown for 3 steels with a lower and a higher nitrogen content, VN2, VN3, and a vanadium steel containing some titanium as well. And you can see that if the holding time, the transfer time is short, then there is a steady decrease in the grain size because the titanium particles assist the formation of vanadium nitride. The higher nitrogen content does the same, and so one is working towards a better structure. Provided that the transfer time is sufficiently long, then this won't matter. We will get a good fine grain size under all the conditions. The result of this treatment is to improve the strength and also the toughness of the final pipe product. Now I'm going to turn to really a completely different aspect of the use of vanadium, one that we've only discovered relatively recently, although it does build on knowledge from many years before in other kinds of steels. And this is in the production of high-strength bainitic strip. So this is strip steels aiming for a yield strength in excess of 700 megapascals by using bainitic structure. Now, the composition that we came forward with is shown here, and the reason for these alloy elements, the chromium, the molybdenum, the manganese, are in order to ensure the hardenability of the steel is adequate, that we will get a fully bainitic structure under the cooling conditions that we're intending to use, and actually the target here was a cooling rate of 30 degrees per second, which is typical for an 8 millimeter thick strip in many steelworks. And what we did was to make extremely small model specimens, only about 1 centimeter high, and we processed them in a deformation dilatometer. The thermomechanical controlled processing schedule is shown here. They were preheated to 1150 degrees, and then they were deformed at 2 different temperatures, 25% each. Of course, in strip rolling you'd have very many more deformations, but we couldn't do that in the laboratory. But this was in order to get the typically refined austenite grain size. They were then cooled at the 30 degrees per second, which is what would happen during the run-out table after the rolling was complete, down to temperatures in the range between room temperature and 600 degrees. When we'd reached the desired so-called coiling temperature, say 400, 500, 600 degrees, we then went to a much, much slower cooling, because at that point the material would be coiled up, it would be losing heat at a much, much slower rate, and 10 degrees per hour was the way we programmed in order to do that. In a practical way, to get 10 degrees per hour in the laboratory, you do this experiment on a Friday afternoon, and on Monday morning it's cooled down. Well, the results are really quite interesting. Here we're going to look at two steels. They have the same base composition. One has a vanadium addition, and the other one doesn't. And these are the yield stresses of our laboratory processed materials. The blue bars here show the strength you get if you cool the steel straight down to room temperature. So not coiling it at any intermediate temperature, hot deforming it and cooling at 30 degrees per second all the way down to room temperature. And you see that they're almost identical. So at this stage, vanadium is not doing anything. It isn't changing the character of the bainite, which is providing the strength here at all. However, if we put in the coiling treatment, which means holding it at a higher temperature for very long periods of time, you see that even at 400 degrees, there is about 100 megapascals loss in strength in the steel without vanadium, and a very small loss of strength in the case with vanadium. If we go to 500 degrees, of course, there's more thermal activation, and the loss is nearer to 200 megapascals, but only a very small loss in the case of the vanadium steel. So in all these cases, irrespective of the simulated coiling temperature, we are exceeding the desired 700 megapascal strength level. To demonstrate this in another way, we took the materials that have been cooled to room temperature and then reheated them to 600 degrees. So that's the blue bars have been reheated to 600 degrees, and we're now looking at the red bars on the right. And you can see again that the vanadium steel has almost the same strength as it had originally, whereas the steel without vanadium is now nearly 300 megapascals softer than it was. So this is a really interesting point. The vanadium is not affecting the original formation of the bainite, but it is affecting its recovery and softening thereafter. That, as I told you, was done on extremely small specimens, about a centimetre long. We did immediately then go to our colleagues in the Swedish steel industry and persuaded them to run exactly the same experiments on full-scale strips of 8mm steel. And they confirmed pretty well what we had found already ourselves in the laboratory experiments. These shows the strength and toughness as a function of the actual coiling temperatures. Now these are the real ones measured in the industry. And up to about 500 degrees, there is very little change in the strength of the steel, and there's very little change in the toughness of the steel as measured by the Charpy values at -40 degrees. Now, this has some practical importance because it's difficult in steelworks to control this coiling temperature at these low values. The thermocouples or the pyrometers do not work reliably down there. But what we've done by having the vanadium in the steel is make a steel which is insensitive to the actual coiling temperature. It's going to give you a good result over a very wide range of coiling temperatures which are not too easy to control. The steel not only had the strength that we were asking for, it had good ductility, it had excellent bendability. That's one of the most important properties of these strip steels. And in other experiments we carried out, we found that the toughness was very good, not only in the metal, but also in the heat-affected zone in connection with welding, which is believed to be a result of the very low carbon content, or rather low carbon content that we have here. This usage of vanadium as a way of slowing down the softening process, slowing down the tempering of bainite, we believe can be applied to other situations. Professor Diardo in Pittsburgh University is looking at applying the similar ideas to dual phase steels, and we ourselves are looking into doing similar experiments with ultra high strength martensitic steels, where we would be looking at strength levels not of 700 megapascals but exceeding 1,000 megapascals, and hoping that we can get similar influences of the vanadium alloying in that case. What I've tried to do here is to summarize several attributes that we see making vanadium a particularly useful microalloy element. It doesn't just do one job, it does several different jobs. And this is a result, to begin with, of its high solubility in austenite. This provides a consistent precipitation strengthening effect. It's a very reliable element in that way. It does as it should do. There's very little interference with the hot rolling, hot deformation process in the austenite range, so we can get an efficient usage of the rolling plant with rapid processing and relatively low loading on the mills. I've shown that there are interesting synergies between the vanadium and nitrogen and carbon and cooling conditions, which allow us to adjust and tailor a very wide range of structures and mechanical properties in the different types of steels. What is relatively new discovery is this strong grain refining effect that can be achieved by the addition of vanadium and nitrogen together through, we believe, the formation of vanadium nitride particles that act as nucleants for the ferrite. The last example I gave is the retention of strength in bainitic and we believe in martensitic structures, which is probably a unique facility of the vanadium alloying. And finally, though I haven't mentioned it at all, we are investigating and have discovered the heat-affected zone toughness in vanadium steels is extremely good under the conditions of welding that are used in the modern low-heat input processes. So this is an attempt to show you how vanadium can be considered as a versatile element. It does many different jobs in the steel. Thank you for your attention.